Hi there, I'm Adolfo Malabanin, and today we're diving into the fascinating intersection between science and cinema. Specifically, we're going to look at gravity and how our understanding of it evolved from the classical world of Isaac Newton to the revolutionary insights of Albert Einstein. But that's not all. Let's also explore how the science of gravity, black holes, and time dilation is portrayed in Christopher Nolan's Interstellar. Is it truly accurate? Could these scenarios actually happen? And most importantly, what's real and what's still science fiction? Let's explore this universe, one equation at a time. For centuries, our understanding of gravity came from Isaac Newton, who saw gravity as an invisible force pulling objects towards one another. His famous law stated that the force of gravity is equal to g, the gravitational constant, multiplied by mass 1 of an object, multiplied by the second mass of the object, all divided by the distance between said objects. And this told us the strength of this gravitational force between two masses. Newton's laws were incredibly successful. They explained planetary orbits, tides, and even the motion of falling apples. But they did have their limits. There was one major issue. Newton could explain why gravity worked. What really caused this force? How does it travel instantaneously through space? And most famously, why does Mercury's orbit shift in a way that Newton's laws couldn't account for? Then came Albert Einstein in 1915, who changed everything with his theory of general relativity. Instead of a force, Einstein described gravity as a warping of spacetime. In his insight, that mass bent the fabric of time and space around it, and objects move along these curves. This idea is captured in Einstein's field equation, where big G U sub V plus lambda G sub UV is equal to 8 pi G over C to the fourth multiplied by T sub UV. Actually, no, all those U should be substituted with mu, but my fault. It is complex, but here's the key idea. The left side represents the curvature of spacetime, and the right side represents matter and energy. General relativity successfully explained Mercury's orbit and predicted gravitational waves. Ripples in spacetime confirmed a century later. Now, let's jump forward from Einstein's equation to Hollywood imagination. Christopher Nolan's Interstellar is a visually stunning film, but how well does the science hold up? Let's look at 4 key scientific ideas portrayed in the movie. First, the spacecraft. The ships in Interstellar, like the Endurance and Ranger, are designed with rotating modules that simulate gravity via centrifugal force, a concept that mirrors real NASA concepts for long-duration space travel. The docking and orbital mechanics scenes are also rooted in reality. They depict realistic inertia, momentum, and the challenge of sinking speeds in orbit. However, the film is vague about the propulsion systems. For real interstellar travel, we would need advanced engines like nuclear fusion drives or antimatter propulsion, technologies that are in still theoretical or experimental stages. One of the film's most mind-blowing ideas is that time dilation near the black hole Gargantua. On Miller's planet, which orbits very close to the black hole, 1 hour equals 7 hours on Earth. 1 hour actually equals 7 years on Earth. This is the real consequence of general relativity. Near massive objects, space-time is so warped that time itself slows down. The closer you are to the event horizon, the point of no return, the stronger the effect. The time dilation formula is stated to be delta t of far is equal to delta t of near over the square root of 1 minus 2gm and that entire thing over rc squared. To get a 1 to 7 year ratio, the planet would need to orbit just above the event horizon of a spinning Kerr black hole. Kip Thorne, Nobel Prize-winning physicist and the science advisor of the film, confirmed that this setup is mathematically possible, but it would require extreme precision and conditions. These conditions would include a supermassive black hole with millions of solar masses, rapid spin to avoid tidal destruction, and a stable orbit in the ergosphere region. So while exaggerated for drama, the concept is grounded in real-world physics. So what would happen if you truly fell into a black hole? In the film, Cooper plunges into Gargantua and survives. Kind of. But how is this even remotely possible? This depends on the type of black hole. For a stellar mass black hole, tidal forces near the event horizon would actually tear you apart, what physicians would call spaghettification. This is when you're being pulled apart and pushed together all at once, and this is basically just getting teared apart. However, for a supermassive black hole like Gargantua, the event horizon is farther out and the tidal forces are much weaker at that boundary. So yes, technically you could cross the event horizon without noticing anything immediately. However, beyond that point, no signals or people can return. Cooper's journey into the black hole's 5th dimension is purely speculative. It is a mix of metaphor, science fiction, and creative storytelling. There is no true evidence that survival or time travel is actually possible within a black hole. Interstellar opens with a wormhole near Saturn, a shortcut to another galaxy. These are based on Einstein-Rosen bridges, valid solutions to Einstein's equations. In theory, a wormhole could connect two distant points in space or time, but there's a catch. These wormholes would obviously be unstable. They would require negative energy or exotic matter to stay open. And of course, in the real world, we've never actually observed such matters in nature. So while wormholes do not actually break any physical laws, they remain in this realm of theoretical physics. The film's visualizations of the wormhole bending space like a sphere is actually quite accurate. It reflects how real physicists model these phenomena using curved spacetime. Thank you for watching. If you enjoyed this journey through the cosmos, let me know what you'd like to explore next. Until then, stay curious and keep looking up.